So far in our coverage of basic electricity, we've talked about what electricity is, how it can be generated, and how it can be used. But we've left out two very important areas, control and protection. And we'll cover those areas in this unit. First, we'll see how we can use transformers to increase or decrease AC voltage so that we can have 500 kilovolts for a transmission line, 110 volts for a lighting circuit, or the exact voltages needed to run any of the plant's motors. Transformers provide one type of control by enabling us to obtain the right voltage for each application. Other control mechanisms that your plant uses include solenoids and relays. We'll have a look at those too. And finally, we'll see how fuses and circuit breakers protect people and equipment from the effects of too much current flowing through a circuit. Okay then, let's start with transformers. Transformers are a very important part of your plant's electrical system. They can increase voltage for high voltage applications, or they can decrease voltage when lower voltages are needed. Let me give you a couple of examples. Suppose your plant's generators produce 15 kilovolts. Now, 15 kilovolts isn't the right voltage for very many applications. For example, the transmission lines leaving the plant typically operate at 200 to 500 kilovolts. So, a transformer is needed to increase voltage from the 15 kilovolts produced to whatever the transmission lines require. On the other hand, 15 kilovolts is too high for most uses inside the plant. For example, the motors in the plant are generally supplied with 4 kilovolts or 480 volts. But you need 110 volts for lights. So transformers are also needed to decrease voltage. Transformers come in many shapes and sizes, but basically they all work the same way. To put it simply, a transformer uses the current flowing in one conductor to induce a voltage in an adjacent conductor. Let's look first at the induction process. Then it'll be easier to understand how the induced voltage is increased or decreased with respect to the source voltage. We've already talked a lot about how to induce a voltage. You know that to induce a voltage by means of magnetism, you have to have a conductor, a magnetic field, and relative motion. You also know that when current flows through a conductor, a magnetic field is created around that conductor. And when the current stops, the magnetic field collapses. So as long as current is flowing through a conductor, there's a magnetic field around the conductor. With a conductor and a magnetic field, we have two of the three requirements for inducing a voltage. In a transformer, the third requirement is relative motion, and that's provided by the building up and collapsing of the magnetic field. If you tried to use direct current to make the magnetic field build up and collapse, you would have to keep turning the current on and off because the magnetic field won't change unless the current changes. However, in an AC circuit, the current is constantly changing by reversing direction. When alternating current flows through a conductor, the magnetic field around the conductor is continually building up and collapsing. So, when alternating current flows through a conductor, the three requirements for inducing a voltage are present: a conductor, a magnetic field, and relative motion. These two wires can show us how the current flowing through one conductor induces voltage in another conductor. This wire is the primary because it's the wire that the source current flows through. When current flows through the primary wire, it induces voltage in this second wire, the secondary. To start things going, we apply AC voltage to the primary wire. Notice that the magnetic field around the primary wire builds up and then collapses. It does this in direct relation to the changes in the current flowing through the primary wire. And as the magnetic field builds up and collapses, it cuts across the secondary wire. And when this happens, voltage is induced in the secondary wire. Now, what we've just seen is quite basically how a transformer operates. current flowing through a primary conductor induces a voltage in a secondary conductor. Now, let's look at the parts of a typical transformer. This transformer has a metal core. The primary conductor and the secondary conductor are coiled around the core. The function of the core is to increase the strength of the magnetic field. We'll get a stronger magnetic field with a metal core than we would if we had just air inside the coils. There are also other reasons for forming the primary and secondary wires into coils instead of using straight wires. When we form a wire into a coil, the magnetic fields around each turn of the wire add together to form one large magnetic field. So the primary is coiled to strengthen the magnetic field. The coiled primary wire is called the primary winding. The secondary wire is coiled to expose more of the conductor to the magnetic field. The coiled secondary is called the secondary winding. There's a direct relationship between the number of turns in each winding and the amount that voltage is changed from the primary to the secondary. For example, if there are more turns in the secondary winding than in the primary winding, the primary's magnetic field will have more conductors to cut across. The induced voltage will therefore be greater than the applied voltage. Now, in this transformer, the primary winding has 25 turns and the secondary winding has 50 turns. Because the secondary winding has more turns than the primary winding, the secondary voltage will be greater than the primary voltage. Well, let's check it out with a voltmeter. When I connect the voltmeter to the primary, I get a reading of 3 volts. Now I'll connect the voltmeter to the secondary and see what I get. Okay, the reading here is 6 volts. The secondary reading is higher. The transformer increased or stepped up the voltage. Now, the reverse of what we just saw is also true. If there are fewer turns in the secondary winding than in the primary winding, the primary's magnetic field will have fewer conductors to cut across. The induced voltage will be less than the applied voltage. Now, this time, I have a coil with 50 turns for the primary winding and a coil with 25 turns for the secondary winding. The voltmeter will read 6 volts for the primary, and since I have fewer turns in the secondary winding, I can expect the secondary reading to be smaller than the primary reading, and it is. It's 3 volts. Now, in this case, with fewer secondary turns, the transformer decreased or stepped down the voltage. Now, there's a formula we can use to calculate what the secondary voltage from a transformer should be. The formula is based on the relationship between the number of primary turns and the number of secondary turns. As usual, the letter E represents voltage. E with a subscript P is the primary voltage and E sub S is the secondary voltage. N is the number of turns that a winding has. N sub P is the number of turns in the primary winding, and N sub S is the number of turns in the secondary winding. In the formula then is E sub P over E sub S equals N sub P over N sub S. Now, to use this formula, we have to know 3 of the values. Let's look at an example. Suppose that we have a transformer that has 10 turns in the primary winding and 5 turns in the secondary winding. This means that N sub P is 10 and N sub S is 5. If the voltage applied to the primary is 10 volts, then 10 is the value we use for E sub P. Okay, let's put the numbers into the formula. E sub P becomes 10, N sub P becomes 10, and N sub S becomes 5. When we work out the math, we see that E sub S, the secondary voltage, is 5 volts. The secondary winding has half as many turns as the primary winding, and the secondary voltage is half of the primary voltage. The formula works when a transformer increases voltage too. For example, suppose a transformer has 10 primary turns and 30 secondary turns. In the formula, N sub P becomes 10 and N sub S becomes 30. If the voltage applied to the primary is 10 volts, E sub P becomes 10. This time when we work out the math, we see that the secondary voltage, E sub S, is 30 volts. When the secondary winding has 3 times as many turns as the primary winding, the secondary voltage is 3 times the primary voltage. We'll be going into more details about how transformers work in the next segment. Right now, though, why don't you read through segment 1 in your text and make sure you understand what we've covered so far. With both step-up and step-down transformers, as we saw in the last segment, one AC voltage is applied to the primary winding and a different AC voltage is induced in the secondary winding. When voltage is applied to the primary winding, current flows through the primary. It's the current flowing through the primary winding that induces a voltage in the secondary winding. Then, that induced voltage causes current to flow through the secondary winding. The power that goes into a transformer on the primary side and the power that comes out on the secondary side are equal. That's an important point to remember. Power in equals power out. When we first talked about power in Unit 2, we said that power is equal to current times voltage. So if a transformer changes voltage, we can also expect it to change current. Because power in equals power out, a change in voltage will mean a corresponding change in current. Well, let's check out these ideas with a couple of examples. This transformer has 1,200 turns in the primary winding and 120 turns in the secondary winding. That makes it a step-down transformer. If we apply 120 volts to the primary winding, the secondary voltage will be 12 volts. The primary winding has 10 times as many turns as the secondary winding, so the secondary or output voltage will be 1/10 as much as the primary or input voltage. Now, let's put this transformer into use so that we can take some readings. We have 2 circuits, a primary circuit and a secondary circuit. Now, the primary circuit is connected to a voltage source and contains a switch. The secondary circuit has a light bulb in it. If the light bulb lights, we'll know that current is flowing through the secondary circuit. When I close the switch, current flows through the primary circuit, the light bulb is lit, so current is also flowing through the secondary circuit. Now, let's take some readings to see if the power that goes into the transformer is equal to the power that comes out. Since power is measured in watts, I'll use a watt meter. Okay, first, we will measure the power that goes into the transformer. Okay, get it connected, on, and it's just about 24 watts. The power coming out of the transformer should be the same. We'll hook up the watt meter and measure that next, right over here. Now, we do, and it is also just about 24 watts. So we were right, power in does equal power out. Okay, now we're going to disconnect things here, and let's see what effect this transformer has on voltage and current. I can use a voltmeter to check the input voltage and the output voltage. The input voltage, the primary, should be 120 volts, and it is. We figured that the output voltage, the secondary, should be 12 volts because the primary winding has 10 times as many turns as the secondary winding, so I'll use the voltmeter to check the secondary. Okay. Right again, the output voltage is just about 12 volts. Now, finally, I'll check the input and output current, and to do that, I'll use these 2 ammeters. First, I'll connect this ammeter to check the input current. Now, the ammeter gives me a reading of 0.2 or 0.2 amps. Okay, I will disconnect the ammeter from the primary circuit. And we will take this ammeter and connect it to the secondary circuit. And when we do that, we can check the output current. The output current is just about 2 amps. The output current is 10 times as much as the input current, but the output voltage is 1/10 as much as the input voltage. Now let's look at why this is so. Power equals voltage times current. P equals E times I. So on the input side, we have 24 watts of power being equal to 120 volts times 2/10 amps. 120 times 2/10 is 24. So it checks out. Now on the output side, we still have 24 watts of power, but we have 12 volts and 2 amps. 12 times 2 is 24. So again, it checks out. When voltage decreases, current must increase, and vice versa. We can also use the power in equals power out relationship along with Ohm's law to calculate current values. This setup is similar to the one we just saw. The source voltage is 10 volts. The transformer primary has 20 turns, and the secondary has 10 turns. So the transformer is a step-down transformer. The number of secondary turns is half the number of primary turns, so we know that the secondary voltage will be half as much as the primary voltage. The primary voltage is 10 volts, so the secondary voltage will be 5 volts. The resistor in the secondary circuit, that is the secondary load, is important because its value determines the secondary current. The resistor in this secondary circuit is a 5 ohm resistor. We can use this value and the secondary voltage value to calculate the secondary current. Now, here's where we need Ohm's law. From Ohm's law, we know that current is equal to voltage divided by resistance. I equals E over R. When we substitute 5 volts for E and 5 ohms for R, we get 1 amp is the value for secondary current. If the secondary current is 1 amp and the secondary voltage is 5 volts, then power out, which is secondary current times secondary voltage, is 5 watts. Power in equals power out, so we know that power in is 5 watts, just like power out. On the primary side, 5 watts is equal to whatever the input current is times 10 volts, which is the input voltage. When we work out the math, we find that the input current is 0.5 amps. That's half an amp. These calculations should help you understand the relationships between voltage, current, and power in a transformer. A transformer increases or decreases voltage. That's its job, because the power coming out of a transformer is equal to the power going into that transformer. The following relationships are true. If a transformer increases voltage, current will be less to provide the same power. If a transformer decreases voltage, current will be greater because power in must equal power out. Before we leave the subject of transformers, there's one more area I'd like to cover very briefly. Transformer cooling. Most electrical equipment heats up as it works, and some means must be found to keep it from overheating. Many transformers, particularly the smaller ones, are cooled by the air around them. With some larger transformers, however, air cannot provide adequate cooling. Most large transformers are filled with a liquid, such as mineral oil or a solution of liquid chemicals. These liquids absorb the heat that builds up as the transformer operates and transfer it to the transformer casing or to an outside heat exchanger. The liquid also acts as an insulator for the transformer windings. Well, by now you should have a pretty good idea of how a transformer works and how to calculate the effects of a transformer on voltage and current. Read through segment 2 in your text and make sure it's all clear to you, and if it isn't, be sure to let your instructor know. In this segment, we're going to look at two types of electrical control mechanisms, solenoids and relays. As you'll see, solenoids and relays operate in much the same way. They both use electromagnets. We've already talked quite a bit about electromagnetism, and you know that we can produce a magnetic field by sending current through a wire. Now, with the aid of a simple demonstration, I want to show you something else about electromagnetism. Here, I have a circuit that includes a battery and a coil of wire and a switch. Now, when I close the switch, I can expect current to flow through the coil, making it an electromagnet. Now, before I close the switch, I'm going to place the coil on some small nails here. And if the coil does become magnetized, it should be able to pick up the nails. Okay, I'll close the switch. Well, what happened? The coil did become magnetized. It picked up the nails. And now when I open the switch, current will stop flowing through the coil. It won't be magnetized any longer, and the nails fall onto the table. Both solenoids and relays work on the basic principle that we've just seen. They both have coils. When these coils are magnetized, other pieces of metal will move toward them. The major differences between solenoids and relays are in how they're constructed and the specific uses to which they're put. Now, let's look at solenoids and relays separately, and we'll begin with solenoids. I'm going to use a coil and an iron core to show you how a solenoid works. First, I'll make the coil a part of an electrical circuit. And having done that, of course that means we can send current through it. The iron core is positioned with one end on the table and the other end just inside the coil. And now, when I close the switch in the circuit, current flows through the coil becomes an electromagnet, and the core is pulled up into the coil. This action is what we call solenoid action. The solenoids in your plant all use solenoid action. Here's a typical example. It's a solenoid-operated valve. When the solenoid is de-energized, spring tension holds the valve stem in the closed position. This graphic will help us to see what happens when the solenoid coil is energized. When current is sent through the coil becomes an electromagnet. As an electromagnet, it attracts the core and pulls it up. When the core moves up, the spring tension is overcome by the solenoid action and the valve is opened. When the coil is de-energized, when current is no longer flowing through it, there is no longer any magnetic force to attract the core. The spring is now able to push the core down, closing the valve. The example we just saw is one way that solenoids are commonly used to control valves. Solenoids can also be constructed so that they cause a valve to close when a solenoid is energized. With this arrangement, de-energizing the solenoid allows the valve to open. Designers must examine each application to determine whether a solenoid valve should open or close when it is energized. The main consideration is making sure systems are kept safe if there is an accidental loss of power. Solenoids are also found in applications other than opening and closing valves. As we'll see later, they're often used in circuit breakers. Brakes on cranes and elevators are two other instances when solenoids may be used. Like solenoids, relays also have many uses in a power plant. Instead of pulling or releasing a core, relays generally open or close contacts. With relays, small changes in voltage or current can initiate control or protective actions of major importance. For example, some relays are designed to sense conditions such as overvoltage, reversal of current, or excessive current. Such a relay is called a sensing relay. When a sensing relay senses the condition it is designed to detect, it operates to provide the necessary protection. For example, a sensing relay might open a circuit breaker or cause an alarm to sound. Other types of relays, called control relays, are used to operate other relays. They're often used in automatic control circuits, in which a small electrical signal sets off a chain reaction of successively acting relays to perform various functions. Control relays are also used in interlocking or interposing situations. For example, We might use control relays to make sure that a pump cannot be started until all its valves are in the proper positions. By interlocking control relays, we can make sure that a reversible motor cannot be energized to run in forward and reverse at the same time. A third type of relay, called a power relay, uses relatively small amounts of electrical power to control much larger amounts of electrical power. Power relays are commonly found in motor controllers, where turning a small switch or pushing a button can start a large motor. The use of power relays is often a matter of convenience and economy. Power relays save space and weight because they allow the use of small switches and lightweight control wires at remote locations. These switches let an operator control large amounts of power at other locations without requiring heavy power cables past the point where they're actually needed. The operation of a relay is a bit different from the operation of a solenoid. In a relay, the core is always in the middle of the coil. The purpose of the core is to strengthen the magnetic field that's produced when current flows through the coil. When a relay coil becomes magnetized, it typically pulls a metal plate to it or causes a metal plate to turn. A relay constructed like this one pulls a metal plate, called an armature, to the coil to operate a contact or a set of contacts. It's the most common type of relay construction. We can see how it works in this simplified graphic. We have two circuits. For convenience, we can call this one the relay circuit and this one the armature circuit. The relay circuit is a coil of wire wrapped around a core. The coil is connected to a power source through a switch. When the switch in the relay circuit is open, no current flows through the coil. The armature circuit includes the armature contacts, a power source, and a light bulb. The armature is held in place by a spring. When the switch is closed, current flows from the relay circuit power source through the coil. The coil becomes an electromagnet and pulls the armature to it. As long as the armature is against the coil, the contacts in the armature circuit are closed. And then current from the armature circuit power source flows through the contacts, and the light bulb lights. When the switch in the relay circuit is opened, current from the relay circuit power source no longer flows through the coil, so the coil releases the armature. With the armature no longer against the coil, the contacts in the armature circuit are open, and current from the armature circuit power source cannot flow through them. Relays like this one are commonly found in power and control applications. This second type of relay is also used to open and close contacts, but it's different from the one we just looked at. This relay has two coils which act as two magnetic poles. The plate above the coils does not actually touch them. The plate is mounted on a rod so that it can turn. There's a contact mounted on the rod. It's a movable contact because it turns with the rod. The other contact doesn't move. It's permanently mounted on some stationary piece of equipment. The operation of this type of relay is similar to the operation of the AC induction motor that we covered in the last unit. When the coils are energized, they induce a voltage in the metal plate, causing it to turn until the two contacts touch. The turning action is normally very slow. Relays like this one are typically used as sensing relays. Fuses are another type of sensing device. We'll be looking at them in the next segment. But before we go on, though, take a few minutes to review what we've said about solenoids and relays. If you have any questions, ask your instructor. Fuses sense high current conditions. They open circuits to prevent components from being damaged by excessive current. The main purpose of a fuse is to provide short circuit protection. When a short circuit occurs, the resistance in a circuit or in part of a circuit drops to almost zero. And as you know from working with Ohm's law, low resistance in a circuit means high current. And high current whether it's from a short circuit or an overload condition, produces excessive heat in a conductor. And that heat can damage equipment, burn insulation, and even start fires. And since excessive current in a circuit is dangerous, some kind of protection must be provided. There must be some kind of a device in a circuit to make sure that excessive current is interrupted immediately. The simplest type of protective device is a fuse. These are many different types and sizes of fuses. They all perform the same basic function. If an excessive current condition occurs, the fuse interrupts the current flow. When this happens, we say that the fuse blows. A fuse is always connected in series with the component it protects. With this type of arrangement, current has to pass through the fuse before it can pass through the component. Now, if current gets too high, the fuse will blow before excessive current can damage the component. In order to carry out its protective function, a fuse must do three things. First, it must be able to sense when an excessive current condition exists. Second, it must be able to interrupt current flow before any damage is done. And third, it must have no effect on the circuit during normal operations. That is, it should just conduct electricity until an excessive current condition occurs. Now, let's look at these three requirements one at a time to see how a fuse does its job. Basically, most fuses are pieces of soft metal called fuse elements contained in a housing. The fuse element has a low melting point. It'll melt at much lower temperature than the wires commonly used in electrical circuits. In an excessive current condition, the current flowing through the circuit and through the fuse is higher than normal. The high current causes the fuse element to heat up until it melts and opens the circuit. And that's what actually happens when a fuse blows. The ability to sense when an excessive current condition exists is in the fuse element. The fuse element responds to the abnormally high heat by melting. The second requirement, interrupting current flow before damage occurs, is closely related to the first. Because the fuse element has a lower melting point than the circuit wiring, the fuse element will melt and the circuit will open before the equipment is damaged. The actual amount of current that a fuse can carry depends on the size of the element and the material from which it's made. The final requirement for a fuse is that it should have no effect on a circuit during normal operation. Fuse elements offer very little resistance to the flow of current through a circuit. As such, they have practically no effect on a circuit unless an excessive current condition occurs. Okay, that takes care of what a fuse does and how it does it. All fuses work in the same basic way, even though there are differences in size, shape, and construction. The two most common types of fuses are plug fuses and cartridge fuses. Here are some plug fuses. A plug fuse is constructed so that it can be screwed into a fuse socket. The fuse element is enclosed in an insulated housing that's usually made of porcelain or glass. You can see the fuse element through the window, made of glass or mica. And since you can see the element, you can tell by looking whether or not the fuse has blown. Now, these are cartridge fuses. We've cut this one in half so you can see the inside. The operation of a cartridge fuse is exactly the same as a plug fuse. The metal element melts when too much current flows through it. The element in a cartridge fuse is enclosed in a tube of insulating material. Now, you can't always see inside a cartridge fuse to tell whether or not the element has melted. Your plant has test equipment like this multimeter that can be used to check a cartridge fuse to see if it has blown. And if you look closely at either a cartridge fuse or a plug fuse, you'll see some rating numbers printed on it. There are two types of ratings for most fuses: current ratings and voltage ratings. The current rating of a fuse indicates how much current the fuse can carry before the element melts and opens the circuit. Current ratings are normally given in amperes. Plug fuses, for example, are usually available with current ratings in the range from about half an amp to about 30 amps. A fuse rated at half an amp will blow if more than half an amp of current passes through it. A 30 amp fuse, on the other hand, won't blow until the current passing through it is greater than 30 amps. A fuse's voltage rating is also important. The voltage rating is the maximum voltage that the fuse can interrupt without having an arc remain across the open section in the fuse element as the element melts. An arc, quite simply, is the flow of current through air between 2 points. When the fuse element melts, an arc forms across the open section. If the voltage in the circuit is higher than the fuse's voltage rating, the arc will not be interrupted and current will continue to flow through the circuit. Some fuses are filled with a material such as sand, which can quench the arc when the fuse blows. Fuses for particular applications are always carefully chosen in terms of current and voltage requirements. For example, you wouldn't put a 15-amp fuse in a circuit that normally carried 20 amps of current. The fuse would blow every time normal current started to flow. You also wouldn't put a fuse rated at 150 volts into a 220-volt circuit because the arc formed when the fuse blows wouldn't be interrupted. You can also have problems if you use overrated fuses. Say a fuse rated at 60 amps is put into a circuit that should carry only 10 amps. The wires in that circuit could overheat and equipment could be damaged before current got high enough to blow the fuse. Current and voltage ratings should be checked whenever you replace a fuse. When you replace a blown fuse, be sure that the new fuse has the right current and voltage ratings. Well, as I said at the beginning of this segment, fuses are the simplest type of protective device in an electrical circuit. In the next segment, we'll be talking about more complicated protective devices, circuit breakers. But first, why don't you take some time to review what we've covered about fuses. And if you have any questions, take them up with your instructor. Like a fuse, a circuit breaker is an electrical protective device that can open a circuit to interrupt current flow. As we saw in the last segment, a fuse element melts to open a circuit when excessive current flows through it. The equipment in the circuit is thus protected from the effects of too much current. But the fuse is damaged and it must be replaced. You can't just reset a blown fuse and use it again. A circuit breaker, however, can be reset after it has opened a circuit. That's one advantage circuit breakers have over fuses. Another advantage is that circuit breakers are better able to interrupt electrical arcs. As I mentioned earlier, an arc is the flow of current through air between 2 points. Air is normally a good insulator, but when it's heated, it can become a conductor. Arcs occur when a switch is opened to interrupt the flow of current through a circuit. This switch is part of a circuit. As long as the switch is closed, current can flow through it. Opening the switch interrupts the current flow, as you know, but let's see what else happens. A switch opens very fast, but we're slowing it down so that we can see what occurs. As the contact points separate, air becomes part of the circuit and heats up. When the distance is very small, the air is very hot. In fact, the air is hot enough to conduct current, so an arc is formed between the contact points of the switch. As the switch opens wider, the arc gets longer. This is a knife switch. Switches like this one were used when people first began to generate electricity. At that time, voltages were quite low. And if someone wanted to open a circuit, he would move the handle of the switch to interrupt the current flow. And if he wanted to close a circuit, he would move the handle in the opposite direction. Knife switches are fine for low voltage applications. They're easy to use. Arcs aren't usually a problem at low voltages. However, as people began to use higher and higher voltages, they found they couldn't keep using these switches. The high voltages produced larger and more damaging arcs when the switches were opened. In fact, if voltage is high enough, a simple switch like this one would continue to arc across even when fully open. Now, this knife switch is part of an electrical circuit. It's closed and current is flowing through it. Watch what happens when the switch is open. An arc forms across the contacts. Now, arcs are undesirable because they create excessive heat, and continuous arcing can damage a switch. In some cases, there may be enough heat to melt the metal that the arc's in contact with. There may also be enough current to electrocute anyone unlucky enough to come into contact with the arc. In addition, the equipment fed by the switch remains energized because current isn't interrupted until the arc is extinguished. There are three general ways to extinguish an arc: distance, cooling, and dielectrics. Distance means increasing the distance between the contact points. As the distance between the contact points increases, the resistance of the air gap between them also increases. From Ohm's law, you know that increased resistance means decreased current. So, as the resistance of the air increases, the current flow that's keeping the arc going decreases. When the resistance gets so high that current can no longer flow, the arc stops. The second way of stopping an arc is to cool the air. Remember, I said that air is an insulator unless it's heated. So if the air is cooled enough, it won't conduct much current. The third method for interrupting arcs uses dielectrics. A dielectric is a material that doesn't conduct electricity. Materials such as oil are used to separate contact points and thus interrupt arcs. And with a switch like the knife switch we just saw, there really isn't any way to stop the arc. There's a limit to the amount that the switch can be opened. So the distance between the contacts can't be increased more than a certain amount. There also isn't much that can be done to cool the air around the contacts. With other switches, however, like most of the light switches in your home and in the plant, distance and cooling are both used to stop arcs. Most of these switches are positioned vertically like this. When the switch is opened, an arc forms just like it did with a knife switch. Because hot air rises, the arc lengthens. If voltage and current are low enough, just the lengthening of the arc will stop it because resistance increases as the arc lengthens. The hot air rises, cooler air surrounds the arc, and the arc stops. This way of stopping an arc is only good for low voltage, low current applications like light switches and small circuit breakers. With higher voltages and currents, it's hard to get enough distance between the contacts to stop an arc. For example, with 230,000 volts, it would take more than 11 feet to stop an arc once it had been established. So, since distance and airflow alone can't stop all arcs, other techniques have been developed. One such technique involves the use of insulating fins, commonly called an arc chute. As the arc rises, it encounters the insulating fins. The arc is forced to move around the fins in order to rise, and the arc is thus lengthened. Cool air around the insulating fins also helps to stop the arc. Circuit breakers that use arc chutes are typically rated up to about 600 volts and 100,000 amps. Some larger circuit breakers use a magnetic field to move the arc and lengthen it until it stops. I can use this glass tube and this magnet to show you how this technique works. This glass tube is filled with a gas. And when voltage is applied to the tube, the gas ignites and an arc forms in the center of the tube. Okay, I'll close the switch. And you see the green light in the tube? Okay, that's the arc. Now, watch it bend while I hold the magnet near the tube. See? The magnetic force from the magnet acts on the arc to make it bend. Now, let's see what happens when we add magnetic force to the arc chute we saw a few minutes ago. With the magnetic field, we no longer have to depend on simple convection to move the arc through the chute. The magnetic field moves the arc rapidly into the chute. Because the arc moves so quickly into the chute, air is able to flow in behind it. This causes a blast of air to flow through the arc. The arc is thus cooled by both the blast of air and lengthened by the insulating fins. This type of circuit breaker may be rated up to about 14,000 volts and 42,000 amps. Another technique for stopping an arc is to separate the contact points in oil. Oil is a dielectric. It's a better insulator than air, so it is more difficult for current to flow through oil than through air. In addition, the arc generates hydrogen gas from oil, and hydrogen gas is a much better cooling medium than air. This circuit breaker uses devices called fiber arc splitters with oil. The arc splitters are enclosed in a chamber. The spaces between them are used as exhaust ports. The fiber arc splitters work like insulating fins to provide resistance to the arc current. Using the fiber arc splitters with oil makes it possible for a circuit breaker to handle higher voltages and current flows for two reasons. First, because the hydrogen gas released by the arc in the confined chamber builds up pressure that increases the resistance of the gas bubbles in the oil. And second, because the pressure causes a blast of hydrogen to pass through the arc. That blast of hydrogen is very effective in cooling and thus stopping the arc. One more way that circuit breakers can stop arcs is to use compressed air. In an air blast breaker, compressed air is blown across an arc to cool and lengthen the arc, faster than any other method we've discussed. The speed of this action is enough to stop the arc. A modification on this technique is to use a gas, such as sulfur hexafluoride, SF6, instead of air. The advantage here is that sulfur hexafluoride is a much better insulator than air. Well, these are some of the most common ways that circuit breakers extinguish arcs. And as we've seen, extinguishing arcs is an important part of a circuit breaker's protective function. We'll be talking more about circuit breakers in the next segment. But before we go on, though, why don't you read through the material in your text and make sure that you understand how circuit breakers can extinguish arcs. And if something's not clear, check it out with your instructor. In the last segment, we saw how circuit breakers can extinguish arcs. Arcs, as we saw, are a natural consequence of opening a switch to interrupt current flow. A circuit breaker is basically a switch, but a switch that has a high interrupting capability. As switches, circuit breakers are often used in the plant to take generators on and off the line. In some plants, they are also used to start and stop motors. Because circuit breakers can protect as well as control, they are widely used. Small circuit breakers are often used in low voltage applications, such as lighting circuits. You might use one like this for a motor. You'll see large breakers in a switch yard. There are many different types of circuit breakers. Some are very simple and some are very complicated. Let's start by looking at a very simple circuit breaker so that we can see what the basic parts are and how a circuit breaker works. This circuit breaker includes two contacts, two springs, and a movable latch. The springs and the latch are what set circuit breakers apart from switches, like the knife switch we saw earlier. When the two contacts are touching, current can flow through them. When the contacts are separated, the circuit is open and current cannot flow. As long as this circuit breaker is closed, the contacts are touching. This spring, that we'll call the contact spring, tries to push one contact away from the other, but the latch keeps that from happening. As long as the latch doesn't move from this position, the contact spring can't push the contacts apart, and the circuit breaker stays closed. When the circuit breaker is closed, current can flow through it. This circuit breaker will open whenever something happens to overcome the tension of this latch spring and move the latch like this. With the latch out of the way, the contact spring pushes the contacts apart, opening the breaker. The breaker stays open until something happens to close the contacts. We'll see how this is done in a little while. In most breakers, the latch spring just returns the latch to its normal position. It doesn't close the contacts. To make it easier for you to see how the contacts operate, we won't show the latch spring anymore. Just remember that as long as the contacts are open, current can't flow through the breaker. Now let's look at some of the ways that the latch in a circuit breaker can be made to move. We'll begin with the three common ways that the opening of circuit breakers can be initiated by an overcurrent condition. The three ways are magnetic action, thermal action, or a combination of the two. In this circuit breaker, there is an electromagnet in series with the circuit breaker contacts. The electromagnet provides for instantaneous opening or tripping of the circuit breaker when current gets too high. If a short circuit occurs, the circuit breaker will open fast enough to prevent equipment damage. This electromagnet works just like all the other electromagnets we've seen. It has a coil and an iron core to make the magnetic field stronger. Current flowing through the coil produces a magnetic field. The strength of the magnetic field depends on the amount of current flowing through the coil. When the magnetic field gets strong enough, the latch is pulled toward the electromagnet. Then, as we saw with the first circuit breaker we looked at, the spring pushes the contacts apart, thus opening the circuit and interrupting the flow of current. This circuit breaker is constructed so that it can handle a certain amount of current without causing the latch to move. But when current gets too high, the latch moves and the circuit breaker trips. Okay, that's one way that circuit breaker openings can be initiated, by magnetic action. The second method involves thermal action. Now, here's a breaker that has a bimetallic strip called a thermal overload in series with the contacts. A thermal overload protects against excessive current, but it doesn't protect against short circuits because it doesn't open the circuit instantaneously like a magnetic action breaker does. Let me show you why. The basis for the operation of a thermal overload circuit breaker is that different metals expand at different rates when they're heated. So the thermal element in this breaker is a strip of two different metals, such as steel and copper, for example, bonded together. Because the bimetallic strip has resistance, it heats up in proportion to the line current. The greater the current flow, the hotter the strip gets. If the current that flows through a thermal overload is too high, the bimetallic strip becomes so hot that it bends. The bending occurs because one metal expands faster than the other. Eventually, unless the current decreases, the strip bends enough to trip the latch, allowing the spring to open the contacts. In some circuit breakers, the bimetallic strips are heated by heater coils positioned next to them, instead of by current flowing through them. The third way that circuit breaker openings can be initiated is by a combination of magnetic action and thermal action. This circuit breaker has both a bimetallic strip and an electromagnet connected in series with the contacts. The bimetallic strip is first. It provides a time delay for momentary overloads, such as starting a motor, because it takes time for the strip to heat up enough to bend and trip the latch. The electromagnet provides for an instantaneous trip if a short circuit occurs. The operation of this circuit breaker is just a combination of the thermal action and the magnetic action of the other two that we saw. This is what it looks like in the tripped position. The circuit breaker openings we've been looking at all occur automatically in response to an overload and/or a short circuit. Circuit breakers can be opened manually, often from remote locations. For example, here's a magnetic circuit breaker like the one we saw earlier, but the electromagnet is connected to a switch and a battery. The switch might be a switch on your control panel, and the battery might be your plant battery. To open this breaker, you would turn the switch. Then current would flow through the coil. Magnetic action would trip the latch, and the breaker would open. Circuit breakers can also be closed from remote locations. We're going to look at three methods that are commonly used to close circuit breakers. First, we'll see a piston operated by air pressure, then a spring, and finally a solenoid. Air pressure closes the contacts in this circuit breaker. When you turn the right switch on the control panel, it opens a solenoid valve to feed air pressure into the cylinder to push on the piston. The piston moves and the contacts close. When the contacts are closed, the solenoid also closes and the air pressure bleeds off. There's no longer any air pressure to push on the piston, so it stops moving. The latch then holds the contacts closed. This circuit breaker has two latches and two springs. Turning a switch at a remote location releases the latch that's holding the contacts open. When that latch is released, the spring pushes the contacts closed. The other latch then holds the contacts closed until the breaker is opened again. The closing spring shown here can be charged by a motor or a cam. This box represents the closing spring charging mechanism. The third method of closing a circuit breaker is to use a solenoid. We talked about solenoids earlier, and we saw how they could be used to open and close valves. Well, they work the same way in circuit breakers. This solenoid is wired to a switch, a battery, and a contact. The contact opens when the circuit breaker closes, and closes when the breaker opens. Closing a switch energizes the solenoid. When the solenoid is energized, it pushes the breaker contacts closed. As soon as the breaker contacts are closed, the solenoid contact opens, de-energizing the solenoid. As with the other breakers we've seen, the latch holds the breaker contacts closed. Well, that about does it for basic electricity. Read through the last segment in your text and make sure you understand what we've covered about circuit breakers and safety. If you need help with your review, ask your instructor.